Okay, this is a video on exponential growth and decay. Just a couple of note pieces if you want to pause your screen and take a look here just to make sure you get some details with exponential growth and decay. First, we're going to talk about the growth model, as you can see here with the plus symbol. So initial amount increasing steadily over time is called exponential growth. Some examples of exponential growth are population growth in an area. Bacteria growth, bacteria grows exponentially, and credit card debt. So the amount that you owe to a creditor, that increases exponentially over time as your debt continues to exist. All right, so here is the exponential growth form for us. Y equals C times 1 plus R to the T power, where Y, C, R, and T are all variables that we have specific names for. Y is the population or the final amount. C is the initial amount, and R is the rate of change in decimal form. So you got to, if it says something changes, at a 30% rate, you have to move that to a decimal. And then T is time. Time is the time period of every increase. So it could be days, months, weeks, hours, minutes, seconds. Depends on what the scenario is telling you. Okay, so if you need to pause your screen and go ahead and get that written down, that's totally okay. I'm going to move into the first example and just try to put this in motion. All right, so the population of Johnson City was 25,000 people in 1995, and since then the population has grown. Okay, so this is going to be exponential growth for us. So that's Y equals C times 1 plus the rate and T for time to the T power. All right, so we're going to go ahead and fill in the information that we know so that we can get it appropriately input in the right locations. So 25,000 people was the population in 1995. Then it started growing from there, and today we're going to look at what the population was in 2015. So that means 25,000 was our initial amount, or our C value. Then it gives you an average rate of 3.2% per year. That's going to be our R percentage. So we're going to have to turn that into a decimal eventually. And you got to do some math on your own. 1995 to 2015 is 20 years. So eventually I'll have to put in 20 for that time, not for the model, but when we do a specific scenario. All right, so here we go. Let's go ahead and fill it out. All right, so the population that I'm looking for is Y. So whatever I plug in for my T value, that'll come back out and give me a Y value, our population. But we know that our C, or our initial population, was 25,000. And then 1 plus, because we're increasing, so that plus is for increase, the rate. So as a 3.2%, is the equivalent of 0.032 as a decimal. If you remember back a little bit further in your math career, you move the decimal place 2 to the left to account for the 2 zeros in 100, or percent, per 100. All right, so 0.032. So multiplying 25,000 by 1 plus 0.032 is going to get larger because that's bigger than 1. And then to the T, representing however many years, T is in years because it's growing every year. All right, so that's going to be our initial model that we're going to use, and we're going to run through these couple scenarios. All right, what is the population in 2005? So that would be a 10-year period. So we would do Y equals 25,000 times 1.032 to the 10th power. All right, so you just grab your calculators and you could type that in, and that will give you what your population was after 10 years. So 25,000 times 1.032 to the 10th power. And my calculations gave me 34,256.026. Well, we're not going to have 0.026 people, so we're going to round down because we can't have a partial person. So 34,256 people in 2005. All right, the next scenario asks us to do it in 2015, so that will be a 20-year period. So Y equals 25,000 times 1.032 to the 20th power for 20 years. Use your calculator for that. 25,000 times 1.032 to the 20th power. And I get 46,939.01. So we're going to just round down to full people in Johnson City in 2015. Okay, let's try another scenario here. And this time I want to run into what it looks like for decay. All right, so decay is the similar model, but instead of 1 plus the rate, it's actually going to be 1 minus the rate, because we need to make sure that we're getting smaller. So when an amount decreases steadily over time, that would be exponential decay. And decay, disappear, decrease, all those words are related. All right, so again, you can see what I was talking about with the minus to make sure that we're getting to multiply by a number smaller than 1. Everything else means the same. Y, C, R, and T all mean the same, but this time we're subtracting as opposed to adding. All right, so let's go and try to pick out important information. All right, the population of Bulgaria has been decreasing at an annual rate, so that's every year, of 1.3, so that's my R, percent. If the population was 7,797,000, that would be my initial amount, or my C value. In the year 2000, predict the current population. Well, making out of this video, it's 2018, so that's going to be 18 years. So for my T value, that's going to be 18 for this scenario that I'm going to do. Okay, so let's go ahead and fill in our model for us here. All right, so Y equals the initial amount, 7,797,000, times 1, and this time I'm paying attention, minus because of decay. 1.3% is the same as 0.013 as a decimal. So that's what's going to take me below 1. So when I'm multiplying, it's going to decrease. And I'm going to do that over an 18-year period. So using my calculator to figure out what my population is after 18 years, 7,797,000 times 1 minus 0.013 to the 18th power. And that gave me 6,160,788.25. So we'll round down to full people in Bulgaria since 2000. Okay? Now, again, I want to emphasize the difference between growth and decay. Growth is getting higher, decay is getting smaller. And the plus and the minus in the model is what is going to help you know if you're getting bigger or getting smaller. So pay attention for that. All right, half-life. That's kind of our next idea here. Half-life is literally the amount of time required to lose half of your initial amount. The amount of time required to lose half of initial amount. And I'm going to abbreviate amount. All right? So we're going to keep this idea of losing half in mind. So let's see if we could work through our information. Keeping in mind that we're still doing some sort of decay because we're losing half. All right, so that's still going to be a y equals C times 1 minus R to the T power. So my approach here is a little bit different. If the organism lived 5,730 years ago, what is the concentration of carbon today? So I'm trying to figure out what the amount of carbon that's left after 5,730 years ago. All right, so an important piece of information that we need to pick up is located in this problem. So the half-life of these living organisms is 5,730 years. Right there, so that's how long it takes to lose half of its mass. And let's say that whatever living organism we're talking about, it started at 100 grams. All right, so whatever I started with was 100, and then I'm trying to figure out, okay, I'm losing half after 5,730 years. Well, I keep saying half, 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 half. Well, what percentage is half? Well, a half is 0.5 or 50%. So this right here, 0.5, is going to be my rate at which I'm getting smaller. So when I go to put that in, that's going to be my R. Okay, my initial amount is right here with the 100 grams, and my time is 5,730. So that's how many years that I'm putting in for T. So that's the number that's going to go in right there. So I'm going to figure out how much is going to be left over, 5,730. Well, I don't even know that I have to do any math for this, because theoretically I should be moving from, this is one half-life, because it says its half-life is 5,730 years. So after 5,730 years, I should be down to 50 grams. Let's see if that's indeed what happens here. Okay, so notice I started to fill in our formula, and I've got the initial amount, I've got the rate put in, and I've got the number of years. But it's a big, like, stop, halt, don't keep going. Because our time increments now are in terms of number of half-lives. That's our time increment. So it's no longer in years. It's in the number of times that I've had a half-life happen. So every 5,730 years in this scenario, that's one half-life. So if they want to know how much is going to be left over after 5,730 years, that's going to be one half-life. So instead of putting 5,730, I should be putting in a 1 right there, because that time frame represents one half-life. So when I go to type this in my calculator, I'm going to put 1 as the T, not 5,730, because half-life problems, the T does not represent years or months. It represents the number of half-lives. Make that adjustment when dealing with half-life. All right, so let's go ahead and see what we get. We expect that after one half-life, we should be down to 50 grams. So in your calculator, 100 times 1 minus 0.5 to the first power, and you get 50 grams. So that's exactly what should have happened. Let's see how we do when they make it a little bit more interesting on this next scenario, 22,920. The first thing you've got to do is figure out what your T is. And your T is not 22,920. Your T is the amount of half-lives. So right away, I'm figuring out how many times does the length of my half-life, 5,730, go into 22,920. So in my calculator, 22,920 divided by 5,730 is 4. So that's 4 half-lives. So that means that I'm going to type in 4 for my T value. So my model for this problem will be y equals the initial amount of 100 grams, and then 0.5 for my rate, because y for 1 minus 0.5 is 0.5. And then now my T value is 4, because that's 4 half-lives. Now I go to put that in my calculator, 100 times 0.5 to the 4th power, and I get 6.25 grams. So after that many years, or 4 half-lives, I've been cut in half and cut in half and cut in half, I'm down to 6.2.